Go ahead and do an example problem. Here we have an insulated piston cylinder device initially contains 300 liters of air at 120 kilopascals and 17 degrees Celsius. Air is now heated for 15 minutes by a 200-watt resistance heater placed inside the cylinder. The pressure of the air is maintained constant during this process. Determine the entropy change of the air assuming constant specific heats and variable specific heats. So again, I'm going to go ahead and start with a schematic. In this schematic, I'm going to go ahead and draw an electric resistance heater. I'm going to make some assumptions. I'm going to assume that my air is an ideal gas. I'm also going to assume that this process is at constant pressure since it's a piston cylinder device, and the piston cylinder device is insulated. So I'm going to go ahead and assume that it is adiabatic. Now, they're asking us to find the change in entropy, right? Now, if you remember, a full second law analysis, right, includes the term entropy change, right? The change in entropy, delta S, the entropy at state 2 minus the entropy at state 1. All of that is equated to the sum of the entropy transfer terms by heat and mass. So I got heat, the sum of the entropy transfer to the system by heat, minus the sum of the entropy transfer by mass, plus the entropy generated. So this system is closed and it's insulated. So if it's insulated, that means there's no heat transfer. Therefore, there's no entropy transfer by heat. And it's closed, so there's no mass crossing the boundary, so there's no entropy transfer by mass. So the problem isn't asking us to do a full second law analysis. It was only asking us to find delta S. But if you were to go ahead and do a full second law analysis, you would find that that change in entropy, that calculation of the change in entropy that we're doing, is actually going to be the total entropy generation during the process. So we'll go ahead and first off, for part A, it's asking us to find the change in entropy of an ideal gas with constant specific heats. So that would be mass times the change in specific entropy. If you remember back earlier in the slide, the correlation for figuring out or for computing the change in entropy of an ideal gas, assuming constant specific heats, is going to be Cp natural log T2 over T1 minus R natural log P2 over P1. Now, this process happens to be at constant pressure, so this term goes to 0, since P2 is equal to P1 and the natural log of 1 is 0. So I find that the change in entropy, which again happens to be Sgen, equals mass times Cp natural log T2 over T1. Now, if we go back to the givens of the problem statement, you'll find that the problem gives us T1. So we have that already, but we don't have T2. So we got to figure out how to compute the temperature at state 2 before we can go ahead and find out what the change in entropy is. So that would require a first law analysis. And again, as I mentioned earlier, typically when you do a second law analysis, it needs to be accompanied by a first law analysis in order to find an unknown that you need. So here we'll go ahead and for this cycle, or for this process, we'll find out. We'll do a first law analysis. E in minus E out equals delta E system. E in is the electric work from the electric resistance heater. Work out is going to be the boundary work. And a change in internal energy will be the change in energy of the system. It so happens that this is constant pressure boundary work. So the boundary work would be pressure times the change in volume. If I go ahead and bring that work term to the other side of the equation, I get delta U plus P delta V, which is equal to delta H, or mass times H2 minus H1. Now, bringing that in use to here, we'll use this correlation to find our T1. I can go ahead, and since I'm assuming constant specific heats for part A, I can substitute delta H as Cp delta T for an ideal gas. I can easily compute the electric work. That would be 200 watts times 15 minutes multiplied by 60 seconds per minute. That should give me the work. The mass is not given to me, but for mass, I can go ahead and use the ideal gas law to figure out mass, right? So I get the initial pressure, which is 120 kilopascals, the initial volume, which is 300 liters, divided by the gas constant for air times the initial temperature in Kelvin for 17C, which is 290 Kelvin. You can do that math and figure out what the mass is. Therefore, at this point, I have the work, I have mass, I can look up Cp, and I have T1, so I can solve this equation for T2, which ends up being 698 Kelvin. And therefore, if I go ahead and I rewrite my equation here, for the change in entropy, it's mass times specific heat times the natural log of T2 over T1. I have mass now, I have Cp, I have T2, I have T1. I can go ahead now and solve for the entropy, which in this case ends up being 0.837 kilojoules per Kelvin. I hope that's clear. Like I said, at this point, I am not going to go ahead and write in all the numbers. You are free to redo these example problems to see if you get the same numbers. But again, this would be for constant specific heats. Now, that was just for part A. Part B is asking us to do the same thing for variable specific heats. So let's go ahead and continue the problem by figuring out the change in entropy for variable specific heat. So we get change in entropy, right? Mass times the entropy at state 2 minus the entropy at state 1, right? Which happens to be equal to Sgen, by the way, according to our second law analysis. So that would be delta S would be the change in entropy for an ideal gas assuming variable specific heat. So it would be S20 minus S10 minus R natural log P2 over P1. Now again, this is a constant pressure process. So due to the fact that it's a constant pressure process, the natural log pressure term goes to 0. And so I'm left with delta S is equal to mass times S20 minus S10. So these two parameters are quantified in table A17. So if you go to table A17, all the properties in table A17 are referenced according to temperature. So for state 1, I can get that my S10 is 1.668 kilojoules per kilogram Kelvin. Now again, that's going to the table and looking at a temperature of 290 Kelvin and finding the the entropy, the temperature dependent portion of entropy. Now, I need to go to state 2. Again, I don't have the temperature at state 2, but if I recall my first law analysis, right, I had that electric work is equal to mass times H2 minus H1. Now I cannot substitute Cp delta T for delta H here because this is variable specific heats. So what I would do is leave it in terms of delta H, and I'll go to the ideal gas table, find H1 according to the temperature, which in this case is 290 kilojoules per kilogram. Take that value, substitute it into this equation, and use this equation to solve for H2, right? So it'd be electric work over mass plus H1. If I did that, I get an enthalpy of 706.3 kilojoules per kilogram. I would now take that H2, I would bring it over to my table. So I'd have an H2 of 706.3 kilojoules per kilogram. And I would go and find my S20 in the table. So I basically go down to enthalpy, find a value of 706.3, and then interpolate for the corresponding entropy value, which would be 2.5626. Again, same units as it is above. And then I can directly determine the change in entropy as mass. So I can go ahead, I'm not going to rewrite that actually, I'm just going to go ahead and reference this. So plug the S10 into the equation, plug the S20 into the equation, use the mass that you solved from the prior slide, and you can get a change in entropy of 0.386 kilojoules per kilogram for variable specific heats, which as for constant specific heats is 0.387. So approximately the same, ever so slightly different.